This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Welcome back to Climate Change, Science and Solutions. This is Chapter 2, where we're diving into one of the scariest parts of climate science: how our warming planet actually speeds up its own warming through something called feedback loops. We'll break down what these loops are and why they make climate scientists lose sleep at night. Let's get into it. The last time Earth warmed this quickly, there were no cities, no highways, no global economy. Yet today's story isn't just more heat. It's how warming quietly rewires the planet's own systems, so that, step by step, the climate begins to push itself. Here's the twist. We're not just heating the planet, we're flipping switches inside it. As temperatures rise, frozen ground starts to thaw, seas nibble away at bright coastal ice, and stressed forests edge closer to collapse. Each of these changes subtly alters how Earth handles energy, what it reflects, stores, or releases, quietly nudging temperatures higher still. Instead of a single thermostat, think of a whole mixing board where one slider affects the others. Thawed soils release gases, which dry forests faster, which invite more fires, which darken surfaces and trap yet more heat. Some processes do push back. Extra heat radiates to space, plants can briefly grow faster, but the balance is tilting. In this episode, we'll trace the main loops that matter, why scientists worry about thresholds, and what this means for the pace of change ahead. To see why feedbacks matter, zoom out from single events, heat waves, fires, floods, and look at timing. The physics of greenhouse gases tells us a slow, steady warming would be expected. What we're observing instead is closer to a series of jolts. Decade by decade, records fall faster than models from the 1990s anticipated, not because the basic equations were wrong, but because many reinforcing loops are now shifting from background noise to active drivers. That's the puzzle of this episode: why a system we once thought would respond gradually is starting to lurch. Not all loops in this story are created equal. Some barely whisper in the background, a few shout. The loudest, in today's climate, are tied to ice, water vapor, and long-stored carbon. Start with ice. Bright snow and sea ice don't just look different from open water or bare rock, they act different in terms of light and heat. As they shrink, satellite records show the Arctic darkening. That shift is big enough that ice loss is estimated to supply roughly a quarter to nearly half of the extra warming there compared with the global average. The key detail: this is happening on human timescales, not geological ones. Summer sea ice extent in the Arctic has dropped by about 40% since the late 1970s, and each missing square kilometer makes the region a slightly more efficient heat absorber the following year. Then there's water in the air. As the atmosphere warms, measurements from weather balloons and satellites confirm it's holding more moisture. That matters because water vapor is itself a powerful heat-trapping gas. Climate models and observations converge on a striking result. This moisture increase roughly doubles the temperature rise you'd get from carbon dioxide alone. In other words, CO2 starts the job, extra humidity leans in and says, "Keep going." Beneath high-latitude ground lies an even slower, more consequential loop: frozen carbon. Permafrost soils contain about twice as much carbon as is currently floating above us in the atmosphere. Field campaigns in Alaska, Siberia, and northern Canada are finding that when these soils soften and slump, microbes wake up and begin breaking down long-frozen organic matter, releasing CO2 and methane. The releases today are still modest compared with human emissions, but models suggest that under high warming scenarios, these regions could shift from net carbon sinks to persistent sources, effectively adding a new, largely unregulated emitter to the global budget. Overlay these with forest stress. Satellite data show that in parts of the Amazon, repeated droughts, logging, and fires are weakening the very system that used to pull massive amounts of carbon from the air. Early analyses hint that some sections may already be nearing a break-even point where they take up no more carbon than they release. Your challenge this week: treat the news like a field log of feedbacks. Each time you see a climate-related headline about ice, storms, droughts, fires, or thawing ground, ask one specific question. Does this change mostly store carbon, release it, reflect sunlight, or absorb it? Jot down just that classification and a brief note. By the end of the week, you'll have a rough, personal map of which loops are starting to move and how often they show up in our collective story. Think of this like tuning an orchestra mid-performance. Touch one section, and the sound of the whole hall shifts. When sea ice shrinks in one corner of the Arctic, shipping routes open, more traffic moves in, and black soot from engines can dust nearby snow, subtly pushing the system further in the same direction. In high mountains, retreating glaciers uncover bare rock where new roads, dams, or mines sometimes follow, locking in different land uses that don't easily flip back if temperatures later stabilize. Even cities get pulled into the score. Prolonged heat can drive higher air conditioning demand, which in many regions is still powered by fossil fuels, adding to the very trend people are trying to escape. On the flip side, some regions are experimenting with feedbacks that lean the other way. Large-scale peatland rewetting in Europe and Indonesia, for instance, cools local microclimates and sharply cuts fire risk, making it easier for those landscapes to stay damp and less flammable over time. Some loops are now intersecting with human systems in surprising ways. Insurance markets, for instance, are quietly redrawing coastlines and fire-prone regions as premiums spike or coverage disappears, nudging where people live and build. Food traders watch shifting rainfall like currency charts as harvest risks ripple through prices. Policy choices can amplify or blunt these ripples, restore wetlands, redesign cities, or redirect shipping routes, and the background loops start to sound different. We're still learning which loops are nimble and which are stubborn, which respond like a light switch and which like a slow-turning ship. That's why every fraction of a degree matters. Each one decides which doors stay closed and which begin to crack open. We can't rewrite the physics, but we can choose whether we lean on brakes or the accelerator. To go deeper, here are 3 next steps. 1. Watch the short documentary series Climate Emergency Feedback Loops, free at feedbackloopsclimate.com. Then pause after each segment, forests, permafrost, oceans, etc., and note one concrete feedback loop you didn't know about, like methane from thawing permafrost or albedo loss in the Arctic. 2. Open Project Drawdown Solutions Library, drawdown.org/solutions, and filter for solutions that directly disrupt feedback loops, for example, peatland protection, tropical forest restoration, refrigerant management. Then pick one and subscribe to or donate to a frontline group working on it, such as Rainforest Foundation US for forest feedbacks. 3. Install a personal carbon tracking tool like Klima or Capture, set your baseline today, and choose at least one action that pushes back on a named loop from the episode, such as switching to a renewable energy provider to cut CO2 that drives Arctic melt, or reducing beef intake to slow deforestation-driven feedbacks. This was OwlUp, your daily step forward. To keep learning with structured courses and more insights, go to owlup.co. Until tomorrow!